Welcome back to the channel, everyone. So today, again, we have another combined techniques question where we have to identify an organic molecule, the structure of an organic molecule that is, using a series of clues, which are mass spec, infrared, and NMR. But today, we don't even have mass spectroscopy to help us. It is just infrared and the NMR. And if we read the question, it says the data and the spectrum shown below were obtained for compound R and has the empirical formula C2H4O. And then if I just scroll down, it just says use the data to provide the structure of compound R. Your answer should identify all relevant data and the spectra that you use. And look at this. Look at the number of marks. 8 marks for this. And we got so little to go on. So before I start, I just want to say I get it. I really do. These questions can be so hard, and I struggled a lot with these in school. But if you have enough practice at them and you follow the exact method that I'm about to outline today, I promise you will get better at these questions and learn to read them quickly and get those full marks. And the method is the same as what I've described in previous videos on this topic, which is you treat each clue as a piece of a jigsaw. So each spectroscopic piece of information you're given, you treat it as a piece of a jigsaw. You put those pieces on the paper and then you assemble them at the end to make the shape of the molecule. So you don't worry too much about what it's going to look like at the beginning. You just get those pieces down, the functional group, the carbon chain, whatever's in there, and you put it together at the end. And then you look at your final picture and then see, does it match in particular what is given in the NMR spectrum? So you circle the environments in your molecule and then circle the environments in the NMR. Do they match? Yes, then you've got it right. So with that said, let's get into it. So normally I say to start with the infrared, which tells us immediately what functional groups are present. So that's what I'm going to do again today. So I can see immediately there is a strong peak, really sharp peak at around 1700, 1750. And as I've said before in my other lessons, it's always the same. There's a Cedar-Bondo. So that's the Cedar-Bondo peak. And then I can also see another peak, which is between 1200 to 1300. And by the way, just a quick reminder, when you read an infrared spectra, look where the red dotted line is going. You look where the peak begins to grow downwards, if you like. You don't take the point, you don't take that bit. It's where it begins to grow down towards the scale. So I can see that's also quite a sharp peak. And if you look at the data table, that is indicative of a C single bondo. By the way, the data table I'm using for the infrared stretches and the NMR is attached in the description below if you want to use the exact numbers I'm using. So I can see that it's got a Cedar-Bondo and a C single bondo. So that is telling me there's 2 oxygens in this formula, even though we're only given the empirical formula at this point, C2H4O. So again, I'm thinking, right, what functional groups have 2 oxygens? So let's start writing down functional groups that have 2 oxygens, and then more broadly, just functional groups that have oxygens. So we have the carboxylic acid, the ester, ketone, aldehyde. And by the way, if it's going to be a ketone or aldehyde, but there's 2 oxygens present in the molecule, there must be some other oxygen functional group further along the molecule. Maybe it's an alcohol, maybe it's an ether functional group, I don't know yet. And then alcohol, as I've just mentioned. So those are like the popular 5. So immediately I can see that there is 2 oxygens, but I don't know whether it's going to be a carboxylic acid or alcohol yet. Or do I? Well, yes, I do. Because in the video I produced on reading infrared spectra quickly, you can look at the shape of the overall spectra and immediately know exactly what functional group it is just based on what it looks like. So I mentioned in my previous video that the alcohol has this double dip and the carboxylic acid has this sort of upside down inverted mountain. Well, you can clearly see this area of the spectrum does not look anything like those. So that's good. So I can rule out carboxylic acid, I can rule out alcohol, and I can now rule out aldehyde and ketone because those functional groups contain just a C double bond O, but I've just shown you that there's a C single bond O because of our peak between 1200 to 1300. So they can go as well. So what does that leave me with? Well, at the moment, it looks to be an ester. So the next thing you need to think about is the NMR spectrum, but I can't really go any further because I don't have the molecular formula, and I need the molecular formula so I can work out the total number of carbons, hydrogens, oxygens, and so on, so I can begin to work out the different environments and how they match the NMR spectrum. So how do we get the molecular formula? Well, I'm just going to recap. Normally you're given the mass spec, and in the mass spectrum you get something called the molecular ion peak, and that peak is the very last peak in the spectrum, at the end of the spectrum that is, to the right, which tells us the mass of the molecule. Well, we don't have that today. We don't even have a mass spectrum. All we have is the empirical formula, which is C2H4O. And then usually then when you're given the molecular ion peak, that is that's the mass of the molecular formula. What you do then is you do the molecular formula divided by the empirical formula, EF, so this is the empirical formula, and it gives you a whole number, which is what you multiply the empirical formula by to work out the actual molecular formula. But I can't do that because, as I said, I don't have the molecular ion peak. But what I'm going to do instead is I can still go ahead and work out the mass of the empirical formula rather. So it's going to be 2 times 12 plus 4 plus 16, and that gives me a total of 44. Now I'm going to show you a trick that you can use to still get the molecular formula, even if you're not given the mass spectroscopy or any other information about it. And for that, we're going to turn to the NMR. But before I do that, I'm just going to quickly recap the rules of NMR for both proton and carbon NMR, which are this. Number one, the number of peaks in the NMR spectra, so distinct peaks, is equal to the number of environments, so proton or carbon environments. Number two, the area under each peak, which is known as the integration, is equal to the number of hydrogens in that environment. And then number three, the greater the electronegativity of the environment, that is equal to a greater chemical shift. So what does that mean? Well, if you have a hydrogen attached to a carbon which is immediately adjacent to a carbon which has, say, oxygens on it, or nitrogen, or fluorine, other electronegative elements, that will make the chemical shift higher. It will drive it to the left, like that. So that is really useful because it allows you to place environments based on their chemical shift, because it's quite common to have the same chemical environments, so say a CH3, and there could be two CH3s in the molecule, but in completely different places because they have different chemical shifts because of the environment is different in electronegativity. So you could have a CH3 attached to an oxygen, which would have a shift of between 3 or 4, and then you could just have a CH3 attached to a regular carbon, part of a carbon chain, which then is going to be further down between like 0 and 1, or like 1.2. So it makes a difference. It makes a big difference, and it helps you spot environments quickly. So I can see that immediately we have a relatively simple NMR graph. There's only 3 peaks, right? This one, and this one. So straight away, I can say that my molecule has 3 environments. And these numbers, which I'm highlighting in blue, these are the integration values. So I can see in the peak to the left, there are 3 hydrogens in that environment. In the peak next to it, there's 2 hydrogens. And in the peak on the far right, there's 3 hydrogens. Now this is really useful for identifying the molecular formula of the molecule, and I'll explain why. So I can say, based on those numbers in blue, that the total number of hydrogens in the molecule is equal to 3 plus 3 plus 2 is 8. So we have 8 hydrogens. Well, our empirical formula, which I'm just highlighting in yellow, shows that we have 4 hydrogens. So look at the relationship between the number of hydrogens in the empirical formula, which is 4, and the actual number of hydrogens in the molecule, which is 8. And what I just said a moment ago, when you divide the empirical formula into the molecular formula, you must get a whole number, which I've just highlighted there. And that is the number you multiply each individual atom by, so this one, and this one, to create the molecular formula. Well, I've just found out that we have 8 hydrogens. So that means the hydrogen must have been multiplied through by 2, which means that is what I need to do for the remaining atoms in the empirical formula. So that gives me a molecular formula, MF, of C4H8O2. So that is the formula we are working with today. Now we've already identified that this is an ester. So let's put this jigsaw piece down. So there's 1 carbon used. So now I've got to work out the remaining 3. And I've used up the 2 oxygens as well. So I've got 1 carbon left, 3 carbons left to work out, and the hydrogens. So for now, I need to turn to the actual splitting patterns in the NMR graph to identify what those environments could be. So the first one that I'm going to deal with is this, as that gives away a big clue. And this has come up in one of the other questions I did in a previous video. So whenever you see a peak that is between 3 and 4, especially more towards 4, so 3.8, 3.9 through to 4.1, 4.2. If you look at the data table, it's always for the same environment, which is a hydrogen attached to a carbon, which is directly attached to an oxygen. So that direct attachment to the oxygen, that is what drives the chemical shift up. Remember what I said about electronegativity? So I can see that there's a hydrogen on a carbon directly attached to an oxygen. And I can see there's 3 hydrogens in that environment. And it's a singlet, which means that it's not adjacent to any other carbons to create the splitting pattern. So what could 3 hydrogens be, which creates a singlet? Well, it has to be a CH3, because they can't be like another carbon like that, which would be 5 bonds. It doesn't make sense. And then if that was possible, it would give rise to like a splitting pattern of a doublet, a triplet, whatever. No, that's impossible. It has to be a CH3. It's a singlet. So that tells me we have OCH3. So let's go back down to our pieces. And suddenly I've got this bit. Okay, we're getting somewhere now, because we've got 2 of the carbons used. We've got 3 of the hydrogens used up and both oxygens. So that just leaves us 2 carbons to put into a molecule. Well, where are they going to go? They have to go here. And now we need to go back to the NMR spectra to see what the splits are for those 2 remaining carbons. So we have the next one. Let me just put this one in green here. That there, you can see if I zoom in. By the way, when you look at the splitting pattern of an individual peak, you have to take every single like sort of blip, if you like. So 1, 2, 3, 4. That is a quartet split into 4, which means the hydrogens in that environment, of which there are 2, are directly attached to a carbon next to it, which have 3 hydrogens. And then according to the n+1 rule, 3 hydrogens next door plus 1 makes a split of 4. So this is assuming you know what the n+1 rule is. It's a technique used to work out the splitting pattern of an environment. So we have 2 hydrogens directly attached to a carbon which has 3 hydrogens, which causes it to split into 4. And I can see that the chemical shift is around 2.4, 2.5. So that fits with a carbon bonded to a hydrogen directly attached to a C double bond O. Do we have that present in our molecule so far? Let's take a look. There it is. And there's 2 hydrogens in that environment. So that fits that perfectly. Now where's the quartet coming from? Well, there's no hydrogens on that carbon, because this is C double bond O, which means the hydrogens must be on this carbon. So there is the CH3. So we have a CH3 next to it, which turns this into a quartet, because it's next to 3 hydrogens there. And And then this one, I'm just highlighting in black here, that is next to carbon which has two hydrogens. So 2 plus 1 makes 3, and that would be split into a triplet. Well, do we have a triplet? Let's go back and look. Yes, we do. 1, 2, 3. So that's the triplet. So our final molecule is, let's draw it more clearly. Let's make some space next to the spectrum so we can discuss. So we have C double bond O with the ester group, CH3, and then carbon there, bonded to hydrogen, and then the CH3 on the end, like so. And then what I'm going to do is circle each environment and match it to each peak in the NMR. So we have this one, let's call it A. We have this one, let's call it B. And then we have the outside one, which is that one, which we'll call C. And now I can assign those labels to the NMR graph. And as I've said before in my previous videos, this is the way to full marks, because if you mess up the explanation, you're not very good with English and writing nice descriptive passages. Like myself, I'm not very good at English. This will get you the full marks because you have proven beyond reasonable doubt that you have got to the molecule without cheating, without fluking it, that you've categorically deconstructed each piece of the NMR spectra and matched it to the molecule you have drawn. So the labels are as follows. A is the CH3 directly attached to the oxygen and is the singlet, so that has to be that one. The quartet is the CH2, so that's B. And then finally the triplet is the one on the end, which is C. So the molecule is methyl propanoate, which, given how difficult some of these questions can be, is actually quite a simple ester. Now the reason why I think it was 8 marks is because we wasn't given that mass spectroscopy information with the relative molecular mass that you normally get, and we had to deduce the number of hydrogens from the proton NMR using these integration values. So that is, I would say, probably going to be 2 marks for that bit of thinking required. But other than that, I don't think that's actually too bad for 8 marks. So you get your molecule, and then, as usual, you just get a bunch of lines. This is where you could do your explanation. And the way you lay out your explanation is you reference your own diagram. You say, environment A is a singlet because it is directly attached to an oxygen, and there's no carbons nearby with a hydrogen, so N is 0, so that's a singlet. The reason why it has an integration of 3 is because there's 3 hydrogens in it. Then you say environment B is a CH2 because it is attached to a CH3 next to it. So 3 plus 1 makes 4. It splits it into a quartet and so on. You just use very simplistic, basic language describing the molecule you've drawn, which is matched to the NMR spectrum. Okay, that's it for today. I hope this has been helpful. Please do like and subscribe. It really helps the channel. And check out the other videos I've made on this topic. Good luck with your revision and see you in the next one.